Welcome to the video lecture in radiation physics. Let's begin with introduction. What is radiation? Mass and energy are two entities that make up our universe. Just like matter, energy is also capable of moving from one point in space to another through particles or waves. The term radiation is used to describe the propagation of energy as electromagnetic waves or subatomic particles through space or through a material medium. It originates from a source and travels through space until it gets absorbed or annihilated by some material. Ever since its discovery, the term radiation has fascinated or frightened many. The trouble is that over the past century, this mysterious and powerful energy has been surrounded by many misconceptions. Hence, it is extremely important to understand the science behind the radiation phenomenon. Classification of radiation. Radiation can be broadly classified into two main categories, non-ionizing and ionizing radiation. Ionizing radiation can be again classified as directly ionizing and indirectly ionizing radiation. Non-ionizing radiation cannot ionize matter because they do not have the sufficient energy to remove electrons from the atoms. On the other hand, ionizing radiation can ionize matter either directly or indirectly. Now, regarding the electromagnetic spectrum, the low frequency waves such as radio waves, microwaves, infrared waves all belong to the non-ionizing radiation category. In contrast, the high energy waves such as the ultraviolet rays, X-rays and gamma rays belong to the category of ionizing radiation. Because the cell phones use non-ionizing radiation, there is no consistent evidence obtained so far that radiation from cell phones causes cancer. Directly versus indirectly ionizing radiation. Directly ionizing radiation have enough energy to pull out the electrons from the orbit of the atom. In such cases, charged particles interact with the orbital electrons via direct Coulomb interactions. Indirectly ionizing radiation does not have enough energy to pull out electrons from the orbit, but they can excite electrons. In such cases, neutral particles interact with matter through two-step process. In the first step, a charged particle is released in the medium. As an example, photons, when they interact with matter, positrons and electrons are released. Now, these charged particles can interact with the orbital electrons of the atoms in the medium, thus causing ionization. Types of ionizing radiation. They include both particulate and electromagnetic radiation. Alpha particles, beta particles, neutron beams and proton beams are the particle beams, whereas X-rays and gamma rays are the electromagnetic waves that can ionize matter. Now let's talk about the sources of radiation. Beginning with natural sources. Cosmic radiation. The radiation reaching Earth from the outer space is called as cosmic radiation. The particles incident at the top of the Earth's atmosphere include all stable particles and nuclei with lifetimes of the order of 1 or more million years. Primary cosmic rays are those which are originally produced in various astrophysical processes. They include protons and alpha particles with a small amount of heavier nuclei and an extremely minute proportion of positrons and antiprotons. Particles produced from subsequent interaction of the primary with the interstellar gas are referred to as the secondary cosmic rays. They include photons, leptons, and hadrons. Once particles from the cosmic flux reach the top of the Earth's atmosphere, the interaction will produce a cascade of particles and the development of cosmic showers. The figure shows the development of gamma ray air showers. Here, the photons interact with the electric field of an atomic nuclei and is completely absorbed, resulting in the production of an electron-positron pair. The electrons and positrons so produced have sufficient energy to produce more photons on interaction with the nuclei. These photons are further capable of bringing about pair production. The result is the generation of large number of photons, electrons, and positrons having a common origin. Now this figure shows the Graves 3 air shower array located at Ooty in India, designed to study the cosmic rays. Cosmic microwave background, or CMB, refers to the low energy photons permeating all the universe and the dominating energy content of radiation coming from beyond our galaxy. The significance of CMB is that they are interpreted today as the remnants of the Big Bang. The early universe was made up of plasma of protons and electrons with thermal electromagnetic radiation. As the universe expanded and cooled, electrons and protons formed neutral hydrogen atoms and radiation could no longer be absorbed. So, they traveled freely and reached the Earth today from all directions. The spectrum of CMB was measured for the first time by the COBE, that is the Cosmic Background Explorer satellite, and it was found to be consistent with the emission of a black body at temperature of about 2.726 Kelvin. The glow is strongest in the microwave region of the radio spectrum. The figure shows the evolution of satellites dedicated to CMB measurements, the COBE, WMAP, and Planck missions. And this shows the progressively increasing resolution of measurements. Solar radiation refers to the radiant energy from the sun. It is composed of electromagnetic radiation, neutrinos from the core, and other massive particles. Neutrinos are produced from the proton-proton chain in the sun's core. The electromagnetic radiation of the sun corresponds to a black body spectrum with temperature of approximately 5776 Kelvin. The three relevant bands or ranges along the solar radiation spectrum are UV, visible, and infrared. Of the light that reaches the Earth's surface, the infrared makes up 53%, while the visible light provides 44%, and the UV radiation makes up 3% of the total solar radiation. Of these three, the UV component of electromagnetic spectrum is the only damaging component. The UV radiation is available in three wavelengths: UVA, UVB, and UVC. The UVC wavelengths range between 100 to 280 nanometers. It can cause the most damage to organisms. However, most of this shortwave radiation is absorbed by the ozone layer. UVB is an energetic radiation that is only partially absorbed in the stratosphere. This radiation band can cause skin cancer in humans. UVA has less energy than UVB and is not absorbed by the ozone in the atmosphere. It can penetrate deeper than UVB and UVC and can reach the retina and can cause retinal diseases in the eyes. Terrestrial radiation refers to the sources of radiation in soil, water, and vegetation. Radioactive materials exist inside soil and rock. Some of the radioactive materials like potassium, uranium, and thorium are ingested with the food and water, while others like radon are inhaled. Internal radiation. Our bodies contain some traces of radioactive elements that expose our tissues to continuous low-level radiation. This internal radiation primarily comes from potassium-40 and carbon-40 isotopes. The amount of radioactivity from potassium-40 contained in about 500 grams of bananas is 65 becquerel. Now coming to man-made sources. The most significant source of man-made radiation exposure to the public is from medical procedures such as diagnostic X-rays, nuclear medicine, and radiation therapy. In addition, we are exposed to radiation from consumer products such as tobacco, television, smoke detectors, and building materials.